Hi there. We have seen thus far that an important application of complex analysis is the ability to take complex geometries and complicated shapes and convert them into something similar by transforming it into a different plane. So this video focuses on a specific type of transformation, that is the Schwarz-Christoffel transformation. So what it does is that it maps a polygon region in the z-plane onto the upper half of the w-plane. So if in the z-plane we have some kind of complex figure like this, and it has some kind of region that's very difficult to work with and describe equations and boundary conditions and so forth, we can take this particular complicated region and we can say that it forms entirely the upper half of the w-plane. So this entire little region inside this polygon becomes essentially the entire plane of the w-plane. That's the top half of it. The second thing about the Schwarz-Christoffel transformation is that it transforms the boundary, and perhaps this is a bit more useful depending on the circumstance. So what it does is that it converts the polygon boundary into a single line, the real axis of the w-plane. So you can take all these different lines and all of this complicated shape, and instead of having a complicated boundary like that, we can transform that entire boundary. We can cut it and we can spread it out. We, for example, cut it and open it out, and it becomes one single line that is on the u-axis, the real axis. So remember that this is the w-plane and this is the z-plane. And we can now take this boundary and open it out and put it on the real axis of the w-plane. So instead of many different shapes, we just have a line. So this video is going to illustrate how to go about doing this. So this is perhaps easiest illustrated to start off with by a simplistic example. Here we have a certain kind of boundary in the z-plane. We have a vertical line, we have a horizontal line, and another vertical line. And there is a region. Yeah, so we're going to take this region and we're going to show how it is the entire upper half of the w-plane and how these different points are simply just points on the real axis of the w-plane, and this entire different line can just be spread out into one single line on the real axis. So what we're going to do is we're going to apply a transformation equation to map these lines and this region into the w-plane. And that transformation equation is that w is equal to minus cos pi z over a. So the question is, how did we know to take this particular transformation equation? So this is what we need to actually come up with, right? We need to find the equation that will transform these lines and this region into what we want. So there is a procedure to follow to find out this particular transformation equation, and we will illustrate that just now, but first we will actually show how this maps onto the w-plane. So we know that z is equal to x plus jy, and we will substitute that in. So when we do that, we get pi into x plus jy, pi into x plus jy, and then divided by a. So we have kind of a double angle here, or rather two angles added together, and you would remember from your trigonometric identities that cos a plus b is equal to cos a cos b minus sin a sin b. So we can substitute that in and apply this trigonometric identity. Here is our a, and here is our b. So this means that w is equal to minus cos, firstly pi x over a, then cos of b, and b is jy over a times pi. So we have j, then pi, then we have y divided by a, then minus sine pi x over A, and then sine B, that's sine j pi y over A. So now we can apply some other identities here. We can get rid of this complex number actually. If we remember our rules or our identities regarding hyperbolic functions, then we would recall that cos of j theta is actually equal to cosh. That's cos hyperbolic of theta. And also we can remember that sine of j theta is equal to j sine hyperbolic or sine theta. And we can now apply these things. And when we do that, we get that W is equal to, we can apply out that minus, so we get minus cos pi x over A. Then we can apply now hyperbolic function. So this will give us cosh pi y over A. Then we have minus, and a minus gives us a plus. So that sine pi x over A remains the same. And then we have hyperbolic function, but remember that j is outside, so we have to write the j in front. So we have sine hyperbolic pi y over A. So if we analyze this, we see that we have a real part, an imaginary part. So that means that u, remember that W is equal to u plus jv. So this first part is u, so we can write that as u. So u is equal to minus cos pi x over A, cosh hyperbolic pi y over A. And also we can see that v, this imaginary part, is equal to sine pi x over A times sine hyperbolic pi y over A. So what we can do is we can now start converting some of these points between the different planes. So let's do it with B and C. So we can see that B is just at the origin and C has a coordinate that's x value A and y coordinate 0. So let's do that. So at B, we can see that x is equal to 0. This is literally the point of origin. And y is equal to 0 as well. So what that means is that when we map it into the W plane, B prime, we get that u is equal to minus 1. We get that by substituting 0 for x and y inside this equation for u. So x is equal to 0, so we have cos of 0. Cos of 0 is minus 1. So we have minus times cosh pi y over A. So we also need to perhaps remember that cosh of 0 is equal to 1 and sine of 0 is equal to 0. So in any case, we have cosh of 0, so that gives us 1. So we have minus 1 and 1, and that's how we get that u is equal to minus 1. And of course, we can see that v is equal to 0 because sine of 0 is just 0. So this entire term is going to be 0. And this is what we want, right? This is what we want. We said that in terms of our mapped variables, we want only the upper half of the plane, okay? And we want this entire boundary to simply be on the real axis. So we want v is equal to 0. So this is u and this is v. We don't want any values of v in terms of these boundaries. We only want it to be on the real axis. So this is something that we are specifically targeting. We can now do this for C. At C, x is equal to A and y is equal to 0. So what this means when we map it is that u is equal to, we substitute in a here, so we have pi a over a. So the a's will cancel off, and we're left with minus cos of pi. And cos of pi, just to remember, is equal to minus 1. So this term gives us minus 1, and cos of 0 is 1. So minus times minus 1 gives us plus 1, and 1 times 1 is 1. So u is equal to 1. And if we look at here, we have sine hyperbolic. Okay, this is a hyperbolic function. Sine hyperbolic of 0 and sine hyperbolic 0 is 0. So this entire thing is going to be 0. Again, this is what we want. We want v to equal 0. So we have our 2 points. We have b prime and c prime, and they are at minus 1 and 1. So we can plot that. So there's b and there's c, and now we have minus 1 and plus 1, and this is where b prime is, and this is where c prime is. So now at this point, what we need to do is map these lines, AB and DC. So when we do that, we can start off with AB. We can see that x is equal to 0. So let's just have a look at it again. So here for the line AB, we can see that x is equal to 0, and y is definitely there. We can see that we have decreasing values of y. So y is coming from infinity, and it's coming to 0. Here between BC, we can see that y is equal to 0, and x is actually going from 0 towards a. So x is going from 0 to a. And then lastly, we have CD. So at CD, we can see that x is equal to a, and obviously it's increasing towards infinity. So y goes from 0 to infinity. So we can just complete that for AB. X is equal to 0. So since x is equal to 0, we can substitute it in for the value of u and v. So when x is equal to 0, we have cos of 0, which is minus 1. So we can see that u is equal to minus cos pi y over a. And of course, v is equal to 0, because we have sine of 0 in v, and then sine of 0 is, of course, 0. So we can see here that y is going from infinity to 0, or y is between 0 and infinity. And when we substitute that in, okay, we can substitute in 0. We have cos of 0. Cos of 0 is 1, so we have minus 1. So that tells us our upper bound is minus 1. And if we put in infinity, we have cos infinity, which is minus infinity, because of the minus in the front. So u goes from minus infinity to minus 1. So what that means is that if we were to plot that on this axis, we are saying that u is going from minus infinity to minus 1. So on this line, it looks like that. So we have a prime to b prime. So this line AB transforms to a prime to b prime, that is minus infinity to minus 1. So now we can do b prime to c, or rather b to c. And when we do that, so we have b to c, and at b to c, we have y is equal to 0. So what that implies, y is equal to 0. And what that implies is that u is equal to minus cos pi x over a. If we just substitute in 0 here, we can see that cos of 0 is 1. So we're left with just the term with the minus cos. And of course, v is equal to 0. And in terms of x, so x that we can see is going from 0 and is stopping at a. So remember at the line BC, x is going from 0 to a. X is going from 0 to a. So we convert that in terms of u and v. So what that means, if we substitute in 0, we have cos of 0, which is -1. And if we substitute in a over a is 1, so we have minus cos pi, which gives us 1. So that means that BC is actually going, transforms to being between -1 and 1 in terms of u. We can actually draw that on our plot. And when we do that, we see that it goes from, u is going from -1 to 1. So that's B prime C. So we can see we have mapped these two vertical lines that are at 90 degrees into one single line. And then lastly, we just have C to D. So let's just see how that is mapped. We can pretty much anticipate that it's going to be also on the real axis because that's what we want. So we intuitively going to see that it's going to go like that. So let's just see that in terms of the numbers. So we have C to D. So C to D. So at CD, x is equal to A. So what that implies when we substitute in A, so we have A over A, that gives us minus cos pi. So this entire thing is going to give us 1. And all we're left with is cosh of pi y over A. Remember that minus cos pi is minus 1. So minus times minus 1 gives us plus 1. So we're just left with this cosh. So we have u is equal to cosh of pi y over A. So in terms of u, well, let's look at the boundary for y. So y is going from 0 to infinity. Y is going from 0 to infinity. So in terms of u is going from 1 to infinity. If we put in 0 here, we have cosh of 0. Cosh of 0 is 1. If we put in infinity, we have cosh of infinity, which is just infinity. We can see u goes from 1 to infinity. So that is exactly what we see. Goes from 1 to infinity. So that's d prime here. So what have we seen? We have seen that we have mapped this entire boundary. We have kind of spread it out and we have put it into one single line. So that has made our work actually much easier. Instead of having a complex geometry or something in which, in this instance, it's more of a simple example. But we can see that we have taken something that was a bit more difficult to work with previously and just made it into a single line. So in terms of the region, so the region is the entire upper half of the W plane. So in this example, what we have done is use the transformation equation, W is equal to minus cos pi z over A. So the original question was, how did we know to use this particular transformation equation? So that's what we're going to see now. If we have a generic polygon in the z-plane with edges AB, BC, and CD, and these points labeled as they are in this picture, and the angles between the different lines, for example, alpha 1 is between A and B, alpha 2 is between B and C, alpha 3, C and D, and so on like that. So what we want to do is map or transform these points A, B, C, D onto the real axis, the u-axis of the W-plane. That means their corresponding maps A prime, B prime, C prime, and D prime have points U1, U2, U3, and U4. So that's what we want to achieve. So we're not going to actually derive this actual transformation. We're just going to show the method as to how it's actually done. So what we want, W over dz, so this is just the method. The derivative of W with respect to z is equal to some constant A into W minus U1, that's U1 here, to the power alpha 1, that's this angle between A and B, over pi, alpha 1 over pi, minus 1. Then we have W minus U2 into alpha 2 over pi minus 1 multiplied by W minus U3 into alpha 3 over pi minus 1, and so on, depending on how much of edges that you have. So what we're going to do is integrate this. So when we integrate it, we get that z, or rather w is equal to the integral. A is a constant, we can bring that out. We have a times the integral of w minus u1 into alpha 1 over pi minus 1 w minus u2 into alpha 2 over pi minus 1. And it carries on like that. It carries on, and the last term will be w minus un to the power alpha n over pi minus 1. And we'll have dw. This is what we're integrating. And then we have a constant of integration, because this is not a definite integral. So we'll have a and we have b. So let's apply this to our case. So if we go to this example that we had originally done, here we have b and c, and here we have this angle. This angle we can see is 90 degrees. It's 90 degrees. And this is also 90 degrees. So this we can think of alpha 1. So alpha 1 is pi over 2. And this alpha 2 is also pi over 2 radians. So let's do that. We can say that alpha 1 is equal to pi over 2, and alpha 2 is also equal to pi over 2. And at these different points, we had chosen u1 to be minus 1 and u2 to be 1. It was on the real axis. So we can substitute these values inside our expression for dw dz. And when we do that, what we get is dw dz is equal to a into w minus, and a minus gives us a plus. So we have plus 1 to the power pi over 2. Remember, that's what alpha 1 is equal to. And then this is divided by pi. And then we have minus 1. So we put that in. And then we have w minus u2. u2 is equal to 1. So we have w minus 1. Again, same thing. Alpha 2 was pi over 2. So we had pi over 2 divided by pi minus 1. So that pi and that pi will cancel out. Same with the second expression there. So we have half. That's what it gives us. So half minus 1 is minus half. And it's the same thing with this second expression as well. So this is equal to a into w plus 1 to the power minus half into w minus 1 also to the power minus half. So this we can write it as 1 over the square root of w minus 1, w plus 1, and we can see that this is equal to 1 over the square root of w squared minus 1. So this is actually equal to w squared minus 1 to the power minus half. So we have a into w squared minus 1 to the power minus half. We just played around with some of the exponents. So anyway, what we can do is take out minus 1 as a common factor. Okay? We take out minus 1 as a common factor because we want 1 minus w squared to the power minus a half. And you'll see why just now. But because we've taken out this minus 1 and all of that, this constant a changes. We can write a new constant k. So this is what dw dz is equal to. The reason why we have written it like this is because this is now equal to k over the square root of 1 minus w squared. So this is a standard integral. Remember that this here is a derivative, and we are now integrating this because we want w. So if we now find w, so w is equal to this integral of k. Let's write it over 2 lines. So we have k over square root of 1 minus w squared. We're integrating this with respect to dw. So what this is a standard integral, right? So this is a standard integral. It means that it's equal to k arc sine w plus I. Sorry, I made an error here. This should have been z. This is z, and it's also z here at the top. So anyway, we have an expression for z. Z is equal to k arc sine w plus I. And what we're now going to do is solve for w. So w is equal to sine z minus I divided by k. So we have to solve for these constants I and k. And to do that, we use these 2 points. Okay, we use B and we use C. So at B, we had z is equal to 0 plus j0. And at C, we had z is equal to a plus j0. So let's just remind ourselves. So here we're talking about B and we're talking about C. So B was just the origin, that's why we had 0, 0. And at A, we have real axis A and no y value. So if we go back down, so we can proceed in this manner. So we had w is equal to sine z minus I over k. So w is equal to actually minus 1. Okay, w is equal to minus 1. Remember that this is the value of u1. u1 is equal to minus 1. Then we had sine 0 minus I divided by k. And then we take arc sine of both sides. So arc sine minus 1 is minus pi over 2. And we get minus I over k. So then what this means is that k times pi, we just cross multiply and express I and k in terms of each other. So k pi is equal to 2i. If we do the same thing at the other side, we have z is equal to 1. This is the value of u2. So u2 is equal to 1. So we have 1 is equal to so this is the expression that we are applying here. So just keep that in mind. So w is equal to that value of u2, so that's equal to 1. And now we have sine z minus I, z was equal to a minus I divided by k. So arc sine 1 is pi over 2, and that's equal to a minus I divided by k. So that means that k times pi is equal to 2a minus 2i. So we can solve for these things, right? So k pi, so that means that 2i is equal to that term. So we have 2i here is equal to 2a minus 2i. So we can just easily solve for I. We see that I is equal to a over 2. Take the 2 pi to the other side. We have 4i is equal to 2a. Divide both sides by 2. So now we have k pi is equal to 2i, so we can bring that here. So that means that k pi is equal to 2 times I, and I is equal to a over 2. So that means that k is actually equal to a over pi. So let's just remind ourselves what w is. W was equal to sine of z minus I over k. So this is equal to sine, we just divide here, z over k minus I over k. And this I over k, let's just do it here, I over k is equal to a over 2, that's what I is equal to, and divided by k. K was a over pi. So this is clearly equal to pi over 2. We have pi over 2. So this term here is pi over 2. So we have sine z over k minus pi over 2. So we're just going to bring this pi over 2 to the front and change the sign. So we have sine of minus pi over 2 minus z over k. So sine of minus the angle is just minus sine of the angle. So we have minus sine pi over 2 minus z over k. So trigonometric identity, sine of 90 minus theta is equal to cos of theta. We use that. So we have minus cos z over k. So we have applied that here. And now this z over k, we can substitute that in. We have minus cos z divided by k, and k we had seen was a over pi. A over pi. That's a divided by pi. And that gives us minus cos pi z over a. And if we look at what our original transformation equation was, okay, so we have just shown it's supposed to be minus cos pi z over a. And let's compare it to what we had used. We go all the way up, then we see that here it is. We can even go more further up. And we had shown it here. This is what we started with. So in summary, what we've illustrated is a certain boundary and how we converted it into a line and also the region. And the second part was showing how we came up with that transformation equation. There was a certain procedure that we had to follow. And this part of the video illustrated that procedure. So thank you very much for watching.